Hello everyone. Today we are going to see about the basics of heat transfer. Heat transfer is the exchange of thermal energy between physical systems due to a temperature gradient. This fundamental phenomena is everywhere in nature and engineering, playing a crucial role in maintaining environmental balance, designing industrial systems, and developing energy efficient technologies. Why heat transfer matters? Heat transfer is critical in applications like power generation, heating and cooling systems, and electronic devices. Understanding the mechanism allows engineers to design better thermal management solution impacting energy consumption and operational efficiency. Mechanisms of heat transfer. Heat transfer occurs through three primary modes: conduction, convection, and radiation. Each mechanism operates under distinct principles and is governed by different physical laws. Heat conduction is one of the primary modes of heat transfer, essential in numerous engineering applications, natural phenomena, and daily life processes. Heat conduction is the transfer of thermal energy through a material without any movement of the material itself. It occurs when particles within a substance interact and transfer energy from high temperature regions to low temperature ones. For example, if you place one end of a metal rod in a flame, the other end eventually becomes hot due to heat conduction. So, the first mode of heat transfer is conduction. Conduction is the transfer of heat through direct molecular interaction within a material. Governed by Fourier's law, it is predominant in solids where tightly packed molecules transfer energy effectively. The rate of conduction depends on the material's thermal conductivity, temperature gradient, and cross sectional areas. For example, heat conduction in a metal cookware is the best example for conduction. The next mode of heat transfer is convection. Convection involves the movement of heat through fluids, that is, liquids or gases, due to the motion of fluid itself. This can be natural convection, driven by buoyancy forces, or forced convection, induced by external means like fans or pumps. Example: heat transfer in a boiling pot of water. The next mode of heat transfer is radiation. Radiation is the transfer of heat through electromagnetic waves. Unlike conduction and convection, radiation does not require a medium and can run in a vacuum. Stephen Boltzmann law describes the radiant heat transfer rate based on the temperature and emissivity of the surfaces. For example, heat from the sun reaching Earth is the best example for radiation. Thermal properties of materials. The effectiveness of heat transfer depends on the thermal properties of materials. The key properties include thermal conductivity, which measures a material's ability to conduct heat. Specific heat capacity, it indicates the amount of heat required to change a material's temperature. Thermal diffusivity relates thermal conductivity to density and specific heat. Emissivity describes a material's efficiency in emitting thermal radiation. Materials with high thermal conductivity, like metals, are used in heat sinks, while insulators like foam are used for thermal barriers. Mathematical modeling of heat transfer. Quantitative analysis of heat transfer is achieved through mathematical models. The key equations include Fourier's law of heat conduction, Q equal to minus Ka dt by dx, where Q is the heat flux, K is the thermal conductivity, A is the cross sectional area, dt by dx is the temperature gradient. Mechanisms of conduction. Conduction occurs at the microscopic level through lattice vibrations, electron transport, and phonons. Lattice vibrations, dominant in non-metallic solids where heat is transferred by atomic vibrations. Electron transport in metals, free electrons facilitate heat conduction. Phonons, quantum mechanical vibrations play a key role in crystalline solids. Thermal properties affecting conduction. Material properties influencing conduction include density, specific heat capacity, and thermal diffusivity. Density. Denser materials generally conduct heat better. Specific heat capacity determines the material's ability to store thermal energy. Thermal diffusivity combines conductivity, density, and specific heat for transient conduction scenarios. Newton's law of cooling for convection. Q equal to HA Ts minus T infinity, where H is the convective heat transfer coefficient, Ts is the surface temperature, and T infinity is the fluid temperature. Stephens Boltzmann law for radiation. Q equal to sigma epsilon A T power 4 minus T power 4 infinity, where sigma is the Stephen Boltzmann constant, epsilon is the emissivity, T is the absolute temperature. Applications of heat transfer. Heat transfer is integral to various fields, including industrial processes, renewable energy, HVAC systems, and electronics. Industrial processes, heat exchangers in chemical plants, and cryogenics for storage of liquefied gases. Renewable energy, solar panels, leveraging radiation, geothermal systems using conduction. HVAC systems, efficient heating and cooling technologies, improve indoor comfort and reduce energy consumption. Electronics, thermal management is essential for preventing overheating in devices. Heat transfer in engineering design. Engineers apply heat transfer principles to optimize system performance. Design considerations include material selection, thermal resistance, and geometric configurations. Case study. Heat exchanger design. Heat exchangers are designed to maximize heat transfer efficiency while minimizing size and cost. Plate heat exchangers and shell and tube designs are common. Advances in heat transfer technology. Emerging technologies are reshaping the field of heat transfer that include nanofluids, phase change materials, microchannel heat sinks, etc. Nanofluids, it enhances the thermal conductivity. Phase change materials, it store and release energy efficiently. Microchannel heat sinks, it improves heat dissipation in compact devices. Challenges and future direction. Despite advancements, challenges remain such as optimizing heat transfer in extreme environments or scaling up renewable energy systems. The future research focuses on integration of artificial intelligence for predictive modeling, development of eco-friendly cooling systems, enhancing heat transfer efficiency in nanoscale systems. Heat transfer is a critical field in science and engineering, influencing energy efficiency, material design, and technological innovation. However, advancing this domain faces numerous challenges and opens new avenues for research and application. The main challenges in heat transfer includes efficient thermal management, high temperature material limitations, nonlinear and multi-physics problems, energy losses in industrial processes, scale dependent heat transfer, environmental impact, and so on. The first one is about efficient thermal management. With increasing miniaturization in electronics, managing heat dissipation in complex systems has become a pressing issue. Devices such as smartphones, laptops, and data centers demand highly efficient cooling solutions to prevent overheating and ensure performance reliability. The next one is about high temperature material limitations. The need for materials that can withstand extreme temperatures without degrading is critical in industries such as aerospace and power generation. Developing materials with both high thermal conductivity and durability remains a challenge. The next one is about nonlinear and multiphysics problems. Heat transfer in real world applications often involves nonlinear behavior and interactions with other physical phenomena like fluid flow and phase changes. Accurately modeling these complex processes requires advanced computational tools and methods. The next one is about energy losses in industrial processes. Significant energy is lost in industrial systems due to inefficient heat transfer mechanisms. Recovering and reusing this waste heat is essential for sustainable practices but presents challenges in designing cost effective and practical solutions. The next one is about scale dependent heat transfer. From nanoscale devices to large scale power plants, heat transfer exhibits scale dependent behavior. Understanding and optimizing heat transfer at both extremes require innovative approaches and experimental methods. The final one is about environmental impact. impact. Cooling systems, especially those using refrigerants, contribute to environmental concerns like global warming and ozone depletion. Some of the future directions in heat transfer includes development of advanced materials, integration of AI and machine learning, base heat recovery technologies, nanotechnology and microscale heat transfer, enhancing renewable energy systems, sustainable and eco-friendly solutions, additive manufacturing in heat exchanger design. Development of advanced materials include innovations in material science such as nanostructured materials, phase change materials, and metamaterials are paving the way for enhanced thermal management. These materials offer tailored thermal conductivity, heat storage capabilities, and improved performance under extreme conditions. The next one is about integration of AI and machine learning. Artificial intelligence and machine learning are ruling heat transfer research by enabling predictive modeling, optimizing heat exchanger designs, and identifying efficient thermal management strategies. Waste heat recovery technologies include developing efficient systems to capture and reuse waste heat, such as thermoelectric generators and organic Rankine cycles can significantly improve energy efficiency in industries and power plants. Nanotechnology and microscale heat transfer. At the nanoscale, heat transfer deviates from classical behavior. Research in phonon transport, nanofluids, and quantum thermal management is uncovering new possibilities for ultra efficient heat transfer mechanisms. Enhancing renewable energy systems. Improving heat transfer in renewable energy systems such as solar thermal collectors, geothermal systems, and energy storage technologies can boost their efficiency and adoption. Advanced cooling and heating solutions are essential for these systems to compete with conventional energy sources. Sustainable and eco friendly solutions. The future of heat transfer lies in developing sustainable technologies that minimize environmental impact. This includes using natural refrigerants, optimizing thermal systems for reduced emissions, and incorporating circular energy principles. The next one is about additive manufacturing in heat exchanger design. Additive manufacturing allows creation of complex geometries for heat exchangers, optimizing heat transfer and reducing material usage. This opens new possibilities for customized and efficient thermal systems. Conclusion. Heat transfer is a cornerstone of thermal sciences, influencing a broad spectrum of industries and technologies. By mastering these principles and applications, engineers and scientists can innovate solutions for global challenges from energy sustainability to advanced manufacturing. Thank you.